Let's start with a cosmic paradox, one that should keep you up at night. Everything you see, everything you've ever touched, everything that makes up you, me, the stars, the galaxies, all of it is only about 5% of what's actually out there. That's right. All the normal visible matter we can detect accounts for just a tiny sliver of the universe. The rest, a whopping 95%, is a mysterious combination of dark matter and dark energy. We can't see it. We can't touch it. But we know it's there because we can measure its gravitational effects on the stuff we can see. It's the biggest mystery in all of science. So what is this invisible majority? For decades we've treated space as the ultimate void, an empty stage where the drama of matter and energy plays out. We call it space-time and describe how it can bend and warp. What if we've got it backward? What if that 95% isn't just dark stuff floating in emptiness? What if space itself is the main event? Imagine space not as a void, but as an active, energetic medium that fills the entire cosmos. It's the ocean, and we, the matter, are just the fish swimming within it. This changes everything. If space is an active player, then maybe it's responsible for some of the universe's most fundamental rules. Think about it. Light travels through space as a wave. Gravity travels through space as a wave. These aren't just properties of light or gravity. They are properties of the medium they travel through. Space isn't just a container. It's a participant. It has properties. It has rules. And if it's the dominant component of the universe, then its rules are the ones that truly matter. Now let's get to the nature of matter itself. In this new framework, what is a particle? Like an electron, like a proton. Let's propose a radical idea, the fixed shell hypothesis. Imagine a tiny, unchanging, rigid shell at the fundamental level, a discrete object, not a fuzzy probability cloud, not a point of infinite density. It has a fixed structure and a fixed size. Once formed, it does not stretch. It does not shrink. Its intrinsic properties do not change, no matter how fast it moves or what forces act on it. Some physics say mass increases near light speed, but what if that's a misinterpretation? With the fixed shell hypothesis, the shell itself remains constant. The effects we measure, like an increase in energy or momentum, aren't happening to the shell. They are happening in the active space around the shell. The shell is rigid. Any change comes from interaction with the external medium. It's a simple, elegant solution to a complex problem. Think of a bowling ball pushed through a tank of thick honey. The bowling ball itself doesn't change. It doesn't get heavier or bigger. The fixed shell hypothesis provides a fresh, intuitive explanation for two of the most fundamental forces we know, inertia, gravity. Let's start with inertia, the resistance an object has to a change in its state of motion. In our standard view, inertia is an intrinsic property of mass. But where does it come from? With our shell model, inertia is not an internal property. It is an external effect caused by the active space pressing against the shell. When you push on a shell to accelerate it, you're also pushing it against the surrounding space, which pushes back. This pushback from space is what we perceive as inertia. The simple and famous equation F equals ma, force equals mass times acceleration, still holds perfectly. M for mass is a constant measure of how much shell stuff is in an object. The force you apply creates the acceleration, but the reason it takes force is that you are working against the resistance of the cosmic medium. The shell doesn't gain mass as it speeds up. Instead, the resistance from space, the pile-up effect, grows exponentially, making it harder and harder to accelerate further. A massive object like a planet is just a huge collection of these fixed shells. Its presence causes a disturbance in the surrounding active space. It creates a sort of pressure gradient or a flow in the medium. A smaller object like a satellite doesn't get pulled by the planet. It gets pushed by the uneven pressure of the space around it, carried along by the flow created by the larger mass. A black hole becomes the ultimate example of this. It's an object with an immense number of shells packed into an incredibly small volume. The disturbance it creates in the surrounding space is extreme. The flow of space toward it is so powerful that it creates an event horizon, a point of no return. The gravity isn't a magical pull from the singularity at the center. It's the overwhelming rush of the cosmic medium itself. Gravity, in this view, is not a fundamental force, but an emergent property of the dynamic relationship between rigid matter and active space. If this model holds true, it completely revolutionizes our ideas about propulsion and the possibility of faster-than-light travel. And current propulsion methods are based on Newton's third law. For every action, there is an equal and opposite reaction. We throw mass out the back of a rocket to push the rocket forward. But this is incredibly inefficient. What if, instead of pushing against our own fuel, we could push against the fabric of space itself? If space is an active medium, then it's something we can potentially manipulate directly. Imagine a new kind of engine, a dual engine system. This ship doesn't have a rocket nozzle. One engine is at the front, another is at the back. The front engine forces the space ahead of the ship to become less dense or to move away, reducing the pileup of resistance. The rear engine does the opposite. It makes the space behind the ship denser or causes it to push forward. The ship itself doesn't accelerate through brute force. It creates a pressure differential, a controlled flow in the cosmic medium, and simply slides along within it. This changes the game entirely. The ship is a rigid shell, remember. It's not warping or bending. The engines are manipulating the space around the ship. This sidesteps the problem of relativistic mass increase because the ship isn't fighting against an ever-growing wall of spatial resistance. It's cleverly getting the space to move out of its way. The universe becomes a story about space, and matter is just a small part of that narrative. This perspective forces us to reconsider what matter even is. If space is the active substance, then matter might be something that interacts with it in a very specific way. Perhaps matter isn't some infinitely complex bundle of fields and particles at its core. Maybe it's simpler. Maybe matter is a sort of disturbance or a knot in the fabric of this active space. To understand the cosmos, we need to stop staring only at the 5% we know and start asking serious questions about the 95% we don't. That's where the real cosmic action might be happening. What if? Time stops at a black hole's edge, but not because gravity grabs it. It's because the road ends. Here's the paradox. Light is the fastest thing in the universe, yet at the event horizon, it doesn't go anywhere. In my quantum physics framing, that's not a prison, it's a power outage. Think of the Higgs field as the conduit that lets light propagate. Time ticks propagate. Zero conductivity means zero motion. At the horizon, the field is under such extreme tension that the conduit vanishes. No path, no passage. I call this the stall state. Not trapped, just nowhere left to go. This flips the usual story. Instead of infinite mass-crushing space-time, I see a finite field failure, a conduit breakdown. The singularity isn't a thing. It's the absence of the thing that carries things. Now, why does that matter for propulsion? If the Higgs field can fail under overtension, it can also be optimized under the right balance. My massless shielding idea treats space as a superconductive medium you can smooth with energy. If I know the exact tension limit where the conduit collapses, I can tune a 4:1 energy to mass ratio to stay perfectly balanced inside the superconductive zone without ever risking field collapse. A black hole is a natural conduit failure. My tech goal is conduit optimization. The hole tears the field, I'd be ironing it flat. Picture it like this. On one side, structural collapse into a fracture. On the other, a craft riding a smooth field, gliding because friction with the conduit drops towards zero. So what about Hawking radiation? In this lens, it's not random quantum leakage, it's the field healing. The universe abhors a vacuum in the conduit itself. The surrounding smooth void pushes on the fracture edge, trying to reknit the field. At the event horizon, the Higgs field is at its breaking point. The rim of the wound. To stitch it back together, the field must reclaim energy from the saturated center. That reclamation shows up as radiation and the byproduct of the conduit taking its territory back, not leaking, repairing, restoring parity one photon at a time. And here's the kicker. If the singularity is field absence, not infinite mass, the mystery becomes mechanics, a limit you can measure, a boundary you can respect. Light and time don't stop because gravity wins. They stop because the highway disappears. Build the road and motion returns. So the paradox resolves like this. Where the conduit fails, clocks freeze. Where the conduit is smoothed, motion flows. And in between, at the edge, the universe is quietly sewing the fabric back together. Relativity is a cornerstone of modern physics, a truly monumental achievement. It gives us two profound rules that govern the cosmos as we know it. The first rule states that nothing with mass can travel at or beyond the speed of light. The second rule tells us that as an object accelerates closer to that cosmic speed limit, its mass appears to increase. These principles have been tested and confirmed countless times in our labs and through astronomical observations. They work flawlessly in most situations we encounter. But what if they are not universal truths? What if they are, in fact, local rules that break down under extreme conditions? The universe offers us a clue in the form of black holes, which suggest a fundamental misreading of a concept known as field tension. This idea does not seek to tear down Einstein's great theory. The mass gain of a speeding object and the absolute speed limit of light might be symptoms of a localized phenomenon. They are effects caused by the way matter and energy interact with the underlying fields that fill all of space. When we push on these fields, they push back. We've interpreted this pushback, this resistance, as an inherent change in the object itself. But the reality could be far more subtle. The mistake lies in assuming the field's response is linear and infinite when it may have limits of its own. Consider the fabric of space-time not just as a geometric sheet, but as an active medium with properties like tension and conductivity. In our everyday experience, this medium is calm and predictable. It allows energy and matter to move through it with a consistent set of rules. However, in the presence of immense gravity or extreme acceleration, this medium can be stretched and stressed to its breaking point. This is where the local mistake occurs. We have applied the rules of a calm, placid field to the chaotic, strained environment near a black hole or a near-light-speed rocket. The black hole, in particular, serves as the ultimate laboratory for this new perspective. It forces us to ask a daring question. Is mass an intrinsic property, or is it a measure of an object's interaction with a field? Our current model says it is intrinsic, but the behavior of black holes challenges this. They show us that an object can contain an unimaginable amount of energy. Let's journey to the edge of a black hole, a place of cosmic extremes. These objects are famous for their incredible density and gravitational pull. A black hole is a tiny region of space containing a vast quantity of matter compressed into an infinitesimal point. It therefore holds a tremendous amount of potential energy. According to a simple interpretation of E equals mc squared, one might expect that as more energy gets trapped inside, its mass would grow without any limit. Yet observations and theories suggest a black hole's mass remains finite and stable for its given size. It does not become infinitely massive just because light and energy are perpetually falling in. The key to this puzzle may lie in a concept called field saturation. Imagine the Higgs field, which gives particles their mass, as a kind of cosmic fluid or a thick unseen soup that permeates everything. In normal, empty space, this soup is thin, and particles move through it with relative ease, acquiring their standard mass. But inside the extreme environment of a black hole, this field is compressed and energized to an unbelievable degree. It is pushed so hard that it reaches a saturation point like a sponge that is completely soaked and can absorb no more water. At this point, it simply cannot impart more mass effect in the way we traditionally expect. This state of saturation changes the rules entirely. The field is full. It has reached its maximum capacity for generating the property we measure as mass. Therefore, even as more energy pours into the black hole, that energy no longer translates into a proportional increase in mass. For decades, we have been told a simple story about why nothing escapes a black hole. Physics textbooks explain that space-time is so severely curved by the black hole's mass that it essentially folds in on itself. Light always travels in a straight line through space-time. Near a black hole, it follows that curve. Near a black hole, all possible paths for the light lead back toward the center. It is a beautiful and compelling geometric picture. But what if there is another way to look at this phenomenon, one that relies on the properties of the field itself? Let's consider the idea of spatial conductivity. Think of the fabric of space as a medium that conducts motion. In the vast empty regions between stars, this medium acts like a perfect superconductor for light. Its conductivity is extremely high. Light travels unimpeded at its maximum speed. There is very little resistance from the underlying field, so kinetic energy propagates effortlessly. This is the universe we are familiar with, a place where light zips across billions of light years. But the environment around a black hole is fundamentally different. The field tension there is stretched to an unimaginable degree that profoundly alters its properties. As the field becomes incredibly tense and dense, its ability to conduct motion could plummet. The road, once a smooth and open highway, becomes a clogged, impassable gridlock. For light trying to leave the black hole, the problem is not that it is being pulled back by gravity in the traditional sense. Instead, The medium through which it needs to travel has lost its conductivity. The field can no longer support the propagation of kinetic energy. The pathway for movement has effectively been closed off. Light is trapped not because all roads lead down, but because there are no roads leading out at all. This perspective changes the very reason light cannot escape. It is not a purely geometric issue of curved paths, but a physical one of a change in the medium. The field itself becomes non-permissive to outward motion, light. Other forms of energy are held in place because the saturated field cannot transmit their kinetic flow. They are stuck, suspended in a region where the universe has lost its ability to let things move. This conductivity model gives us a new physical mechanism to explain the event horizon. It complements the geometric one and grounds it in the behavior of quantum fields under extreme stress. Now let's leave the black hole behind and consider a much more familiar object, a rocket ship accelerating through space. According to special relativity, as the rocket approaches the speed of light, an outside observer would measure its mass as increasing. Pushing it further requires more and more energy until it would take an infinite amount of energy to reach light speed. This effect has long been called relativistic mass gain. But this term may be deeply misleading. It mixes up two very different concepts: the intrinsic mass of the rocket, the resistance it feels from the field it is moving through. The rocket ship itself is not actually getting heavier. Its internal composition, the number of atoms it's made of, does not change. What changes is its interaction with the local space around it. As the rocket pushes forward with tremendous energy, it creates a disturbance in the underlying quantum fields, like the Higgs field. It effectively drags the local field with it, creating a region of increased tension and density in its immediate vicinity. This increased field tension acts like a form of cosmic friction or drag. It pushes back against the rocket, making further acceleration more difficult. From the outside, this increased resistance looks exactly like the rocket has gained mass. It behaves as if it is heavier because it takes more force to get the same amount of acceleration. But the change is not inside the ship. It is in the field outside it. The ship is experiencing an induced resistance from the medium it is plowing through. This is a crucial distinction. The rocket does not grow heavier with more particles. Instead, the field it is interacting with becomes tighter and more resistant to its passage. This is a local field effect, not an intrinsic property change of the object. This perspective helps resolve the seeming paradox of mass gain. The energy being pumped into the rocket's motion is not being converted into new particles of mass within the ship. Instead, that energy is being spent to fight the increasing tension of the field. The mass gain is a measurement of this struggle, a measure of the field's resistance. It is an external effect, a property of the interaction between the object and space, not a property of the object alone. By separating the idea of true internal mass from this induced field resistance, we get a clear and more physical picture of motion at high speeds. The black hole stands as the ultimate bold example that separates energy from mass under extreme conditions. Let's bring the ideas together. If Einstein's famous equation, E equals mc squared, were a simple, direct, and universally linear conversion law, then a black hole would present a major paradox. A black hole is a place where an immense amount of energy is confined within a small space. Its own internal pressure and the continuous influx of matter and radiation from the outside contribute to a staggering energy density. If all of that energy were directly converted into mass, the black hole's mass would grow without limit, becoming truly infinite. But that is not what happens. A black hole remains a finite, stable object. It is a deep gravitational well, but it is not an infinitely massive one. This simple fact is our most powerful clue. It demonstrates that under the extreme tension found within an event horizon, the relationship between energy and mass changes. The equation does not apply in the same way. The black hole proves that an object can contain and process colossal amounts of energy without that energy manifesting as a proportional runaway increase in its mass. The system reaches a state of equilibrium dictated by the properties of the saturated field. This provides a clear distinction between two types of energy. There's the energy that constitutes the rest mass of particles, which contributes directly to the object's gravitational footprint in a calm field. Then there's the kinetic and potential energy bound up within the system, like the motion of particles and the pressure of radiation trapped inside. In a black hole, this second kind of energy does not continue to add to the mass total indefinitely. The saturated Higgs field simply cannot support the conversion. The energy is there, but its gravitational effect is capped. This is why the black hole is so revolutionary to our thinking. It is a real-world object that forces us to confront the limits of our equations. It shows that energy and mass are not always two sides of the same coin, especially when field tension reaches its maximum. The black hole acts as a cosmic regulator, holding immense energy in a stable configuration without turning that energy into infinite mass. This behavior is impossible to explain if mass gain is a simple and direct consequence of added energy. It only makes sense if there is an underlying field mechanism, like saturation, that changes the rules of the game. The lessons from the black hole compel us to adopt a new, more nuanced perspective on the rules of the cosmos, the cosmic speed limit. The concept of relativistic mass gain are not incorrect. They are incredibly successful descriptions of reality within the normal low-tension conditions that prevail across most of the universe. They are, however, local rules for a placid field. When we push the fabric of space to its absolute limit, as a black hole does, these rules appear to break down. This is not a failure of relativity, but an invitation to deepen our understanding of it. The central takeaway is that energy and mass are not always directly and linearly proportional. The relationship between them is mediated by the state of the underlying quantum fields. When the Higgs field is calm, E equals mc squared works as expected. But when the field is pushed to a state of saturation, its properties change. It can no longer translate added energy into added mass effect. This is the secret the black hole reveals. Its finite mass, despite its infinite energy appetite, is the proof. Similarly, the mass gain felt by an accelerating rocket is better understood as resistance from field tension, not as an intrinsic change in the rocket itself. This revised thinking opens up exciting new avenues for exploration. If the conductivity of space is a variable property, we can start to model trapped light as a problem of flow and resistance, not just geometry. This could simplify our understanding of event horizons and other